Imagine an AI that doesn't just, output a Python script and just hope for the best.
Right, the classic zero shot and pray approach.
Exactly. But instead, it actually runs the code, reads its own execution logs, debugs the errors, and incrementally rewrites its entire architecture.
Which sounds like science fiction.
It really does. And it does all of this locally on a single consumer graphics card. That is exactly what we are unpacking today on AI Paperslop.
It's a massive breakthrough.
It is. We're looking at a paper titled Frontis-MA1, Training an AI4AI Model Towards Recursive Self-Improvement in Machine Learning Engineering. This is from Horizon Research, Frontis.ai, and Tsinghua University.
Yeah, and if you build AI systems, the core insight you need to know immediately is that the authors are using machine learning engineering, or MLE, as a fully executable testbed for recursive self-improvement.
Right. They introduced this thing called the OpenMLE stack, and they train a model called Frontis-MA135B as a meta-evolution agent.
And the results are, frankly, staggering.
They really are. By relying on just 4 atomic operators, draft, improve, debug, and crossover, and a long-horizon search framework called OpenMLE Evo, they took a 35 billion parameter-based model from a 39.39% metal average on MLE Benchlight all the way to 71.21%.
That's a massive jump.
Huge. And they achieved this with a 12-hour per-task compute budget on a single RTX 4090, capped at 12 gigabytes of VRAM.
Which is wild. It's competing with, or frankly beating, massive models like GPT 5.5 and Claude Opus 4.8.
Yeah, and it's approaching the 2.8 trillion parameter Kimi K3. It just proves that test time scaling is exponentially more powerful when you transform it into actual test time learning through execution feedback.
Exactly. And if you dig into the architecture, the true elegance of this paper is how it cleanly separates the local skills learned by the model from the search algorithm used at inference time.
Right, because usually they're all tangled up.
Yeah, exactly. The system isn't trying to learn how to search a massive solution space and how to write PyTorch code simultaneously in some unstructured way.
Which usually just leads to disaster.
Totally. It usually leads to this really sparse controller-specific supervision where the model just gets confused. Instead, it learns highly specific, reusable, evolutionary behaviors. Then, this external search framework figures out how to compose those behaviors to actually solve the problem.
Okay, let's unpack this because I want to break down exactly how they achieved that separation. The concept of recursive self-improvement, RSI, has been tossed around for years as this theoretical, almost sci-fi endpoint.
Yeah, people always say eventually the AI will just write better AI.
Right. But to build that in reality, you need a place for the AI to practice. If you want an agent to improve at machine learning engineering, you can't just have an LLM spit out text and use another LLM as a judge and say, yeah, it looks good to me.
Right, it has to be grounded in actual execution.
Yes, grounded in execution. And that brings us to the foundation of their stack, which they call OpenMLE Gym.
Yeah, because if you don't ground the code in execution, you are just optimizing for plausible-sounding syntax.
Which we see all the time.
Exactly. So OpenMLE Gym is an open full-stack system that actually converts Kaggle competitions into standard executable packages.
Now, we all know Kaggle, but I'm really curious about the filtering process here.
Yeah.
Because you can't just scrape the entire MetaKaggle catalog.
Right.
What is it, like 11,000 competitions, and just feed it to an AI?
No, absolutely not. A lot of those competitions have broken data sets or deprecated dependencies.
Or completely ambiguous evaluation metrics.
Yeah, that was actually the first major engineering hurdle the researchers solved. They built an automated pipeline to standardize the catalog, but they applied a very strict semantic quality gate.
Okay, what were they checking for?
They were checking for task validity, ensuring the data sets were completely sufficient to actually run the code, and analyzing task complexity. They managed to filter that massive list down to just 2,240 high-quality executable tasks.
Wow. And the distribution of those tasks is what really caught my eye. 44% of them are tabular data, 18% are image-based, and 13% are time series, plus some text and multimodal tasks.
Yeah, that tabular heavy mix is super important.
It makes a lot of sense, right? Because that is notoriously where automated machine learning agents usually hit a brick wall, handling messy, real-world CSV files with weird categorical variables. That requires a lot of architectural intuition.
Exactly. But having the data is only half the battle. You also need an environment where the agent can run its code without, polluting its own workspace.
Oh, this is where the execution backend comes in. And I think anyone who has ever wrestled with local Python environments will appreciate this.
Oh, absolutely.
They didn't just write a local script to execute the model's output. They built a centralized scheduler that routes API requests to CPU and GPU Docker workers. So it's almost like giving the AI its own mini AWS infrastructure.
Yeah, that's a great way to put it.
When the AI wants to test a hypothesis, the system materializes a completely isolated ephemeral cleanroom. It mounts the data, runs the code, captures the exact score, writes all the artifacts and logs back to shared storage, and then destroys the environment.
You absolutely need that hermetically sealed environment for reproducible scoring. Because if you're doing long horizon search, meaning the AI is iterating on a problem for 12 hours, state contamination is your biggest enemy.
Right, like an undeclared variable just hanging out in memory.
Yes. If the AI tries a new hyperparameter or tests a new loss function, it has to know with absolute mathematical certainty that the change in the score is due to its code, not because a previous run left residual junk in the GPU memory or altered a local file. Separating the control, the execution, and the storage guarantees that the test time learning is grounded in reality.
Okay, so we have this pristine ephemeral cleanroom. The mini AWS is there.
Right.
But an empty cleanroom doesn't do the work.
What is the AI actually doing when it boots up?
Right. That brings us to the OpenMLE RL component.
The reinforcement learning of evolutionary operators. And I have to be honest with you, when I first read this part of the paper, I immediately thought it was a mistake.
Really? Why?
Because they restricted the AI to just 4 specific atomic operators: draft, improve, debug, and crossover. Yeah, let me define this quickly for context. Draft creates the initial code from scratch. Improve refines an already working solution to try and squeeze out a better score. Debug repairs code that crashed or threw a syntax error. And crossover merges 2 completely different parent solutions into one child solution.
Right.
Yeah.
And here's where I get stuck, right? You're taking a 35 billion parameter model. We know from interacting with frontier models that they are incredibly capable of outputting massive free-form trajectories.
Sure.
You can just prompt them to stream out code, read their own console outputs, dynamically pivot. Why would you nerf a model of that size by restricting it to 4 specific buttons?
Yeah.
Why not just let it output free-form code sequences and figure out the workflow organically?
I get that. It seems like an artificial bottleneck.
Exactly.
Well, what's fascinating here is that this constraint is exactly why it works. It's the exact mechanism that solves the credit assignment problem in reinforcement learning.
Okay, how so?
If you've ever tried to train an RL agent on long horizon coding tasks, you know that the reward signal is incredibly sparse.
Because, if the model outputs a 100-step interaction, and on step 99 it throws an out-of-memory error, the model just gets a 0 score. But how does it know if step 4 was the brilliant part and step 98 was the mistake?
Precisely. If you let it output free-form trajectories, the model doesn't know what to learn from the failure. By forcing the model to interact strictly through these 4 atomic program evolution operators, you're standardizing the action space.
Oh, I see.
The model isn't learning how to solve a Kaggle competition. It's learning highly isolated skills. It learns the specific statistical patterns of, how to write a robust first draft or how to ingest a key error and patch those specific lines.
So it's building a repertoire of reusable tools rather than trying to memorize a monolithic workflow.
Yes. It avoids sparse controller-specific supervision entirely. And the researchers trained these operators rigorously. They used execution-grounded supervised fine-tuning, or SFT, followed by reinforcement learning.
Do we know how much data they used for that?
Yeah, the SFT corpus alone contained 26,259 examples. That breaks down to about 17,000 full draft rollouts and over 9,000 evolutionary steps, like debugging and improving.
Wow. And crucially, all of this data was strictly deduplicated against the evaluation benchmarks.
Which is vital, because if you have benchmark contamination, your results are completely invalid. You're just testing the model's memory, not its intelligence.
Right, it would just be cheating.
Yeah.
So the model is heavily fine-tuned to be an absolute specialist in drafting, improving, debugging, and crossover. But doesn't that introduce a massive routing problem for the system as a whole?
It does, yeah.
If you give the system a 12-hour compute budget per task, how does it decide which of those 4 tools to use at any given moment? Like if a script fails, does it debug? Or does it scrap it and draft a new one? How does it avoid getting stuck in a 12-hour infinite loop of just failed syntax repairs?
That routing problem is solved by OpenMLE Evo, which is their long-horizon search framework. This is where we shift from the model's localized actions to the system's overarching logic. Most naive agent frameworks just use greedy search. They look at the current tree of attempts, pick the one with the highest score, and tell the model to improve this.
But if you just greedily optimize the highest score, you're going to hit a local optima almost immediately. You'll overfit to whatever architecture you drafted first, like maybe your random forest, and you'll just spend hours tuning hyperparameters while completely ignoring the fact that a neural network would have fundamentally solved the problem better.
Exactly. OpenMLE Evo avoids that by using a multi-factor selection process based on experience. It doesn't just look at the current quality of the node, it looks at progress, meaning what is the delta versus the parent node. Is this specific branch actually yielding improvements, or has it plateaued? And even more importantly, it evaluates novelty.
Wait, how does it measure novelty in a code base?
It looks at the algorithmic direction the branch represents. Is it a new direction entirely? If a branch is trying a completely new ensembling technique, the search framework will allocate compute budget to it, even if its initial score isn't the highest in the tree.
That's smart.
By balancing quality, progress, and novelty, you maintain selection pressure toward high-quality solutions without starving underexplored approaches of compute.
But for the search framework to evaluate progress and novelty, it needs memory. It needs to know what has already been tried. And I really want to dig into how they implemented this, because it solves a massive problem in agentic coding.
Oh, the context window issue.
Yes, if you've built an AI agent before, you've probably hit the context window limit. A typical Python error log with deep stacked traces could be thousands of lines long.
Right.
If you just eager load the raw logs of every failed attempt into the LLM's context window, you blow up the token count, and the model completely loses the plot due to the needle in a haystack problem.
Right. Raw logs are low signal, high noise data. So OpenMLE Evo uses a technique called operation-triggered memory synthesis.
Operation-triggered memory synthesis.
Yeah. Instead of dumping raw logs when an operation is selected, the system retrieves a bounded set of relevant past experiences. It then uses a memory model to synthesize that raw data into two structured JSON fields: method overview and parent comparison experience.
The analogy that popped into my head when I was reading this is the difference between a junior developer and a senior developer using Git.
Okay, I like where this is going.
So a junior dev might push a 10,000-line diff to the repository, and their commit message just says, fix bugs.
Which is completely useless if you're trying to figure out what they actually did.
Exactly. But a highly disciplined senior engineer writes an incredible, meticulous commit message. They explain exactly what structural changes were made, why a specific physics feature was added, what happened to the validation score, and what to avoid that they already tried. That is essentially what these JSON fields are doing for the AI.
It's a great way to think about it. The method overview field provides a concrete, high-level description of the features, the ensembling methods, and the validation strategy of that specific node. You don't need to read the 500 lines of code to know what the code is doing.
Right.
And the parent comparison experience provides an evidence-based account of the delta between the parent and the child node. It explicitly notes what changed, what improved, and synthesizes a direct instruction on what should be reused or avoided in the next step.
So because this synthesis is cached, when the AI wants to iterate on a branch 3 hours later, it doesn't have to reanalyze raw error traces or full code bases. It just reads these highly disciplined commit messages.
Exactly. It keeps the context window incredibly lean, but packed with high-signal, actionable evidence.
That structural discipline, both in the restricted atomic operators and the synthesized memory, is what actually enables the massive performance gains we see in the results.
It really is the secret sauce.
Here's where it gets really interesting. Let's get into those hard numbers, because this is where the theory proves itself. They benchmarked this on MLE Bench Lite. The base model, before all this execution-grounded training, was Qwen 3.635B A3B.
Right.
With a standard setup, that base model scored a 39.39% metal average. After post-training it into Frontis-MA1 35B and running it through the OpenMLE Evo search framework, it jumped to 60.61%.
Which, just on its face, is an incredible delta for a 35 billion parameter model.
But they didn't stop there. They introduced OpenMLE Evo Max. From what I understand, Evo Max adds benchmark-independent experience priors and uses asynchronous search, basically optimizing the parallel execution across those Docker containers.
Yeah, and giving the model better starting heuristics based on past general experience.
Right. And with EvoMax, the model hit 71.21% metal average.
To contextualize, a 71.21% score on MLE Benchlight. This system is beating GPT 5.5 paired with Codex. It is beating Claude Opus 4.8, and it is approaching the performance of GPT 5.6 Sol and the 2.8 trillion parameter Kimi K3.
That's insane.
You have a model that fits on a single consumer-grade RTX 4090 GPU going toe-to-toe with trillion parameter behemoths that require massive data centers to run.
That efficiency is wild. But what I find even more impressive is what they call the gold shift.
Oh, yeah!
This is crucial. The researchers point out that the system isn't just brute forcing its way to a higher average by sweeping up a bunch of easy bronze metals. It fundamentally shifts the quality of its solutions toward gold metals. It actually matched Kimi K3's gold rate and beat Gemini 3.5 Flash, running the Gemini CLI. It is genuinely solving the hardest algorithmic problems in the benchmark.
And if you want to understand mechanically how it secures those gold metals, the paper provides a brilliant case study on the crossover operator.
Well, this was my favorite part.
In program evolution, crossover is notoriously the hardest operation to pull off.
Oh, without a doubt. I mean, merging two code bases written by human engineers who sit right next to each other usually results in a syntax nightmare. How does an AI merge two entirely different structural approaches without just creating a Frankenstein script that immediately throws a compilation error?
It's really tough. But the paper highlights a specific task called Nomad 2018 Predict Transparent Conductors.
Okay.
It's a materials science competition where you have to predict the properties of transparent conductors based on complex tabular data. The baseline system, running a standard debugging loop, hit a complete wall. It got tunnel vision on a single lineage of code and was trapped in an endless loop of nested mapping errors while trying to process the data structures.
Because it was only using greedy search, it couldn't back out of the dead end.
Exactly. But OpenMLE Evo didn't have tunnel vision. It looked at the broader search tree and identified two distinct, promising branches that had been kept alive by the multi-factor selection process.
So what were the branches?
One branch had successfully developed a physics graph neural network, a highly sophisticated architectural concept for materials science. However, it was struggling with data processing. Another branch had developed a robust parser that successfully handled the messy nested tabular data without crashing, but its model architecture was just too basic.
So the search framework says, let's combine these.
Yeah.
But again, how does it physically stitch them together?
It relies on that operation-triggered memory synthesis we talked about earlier. The crossover operator didn't just blindly copy and paste code from script A to script B. It ingested the method overview from both branches.
Oh, I see.
It understood the conceptual logic of the robust flat mapping from the parser branch and the conceptual logic of the physics features from the GNN branch. It then essentially drafted a new child script that fused those paradigms logically. Furthermore, because it read the parent comparison experience, it explicitly knew to avoid specific sibling failures it observed nearby.
The result was a structurally distinct child code base that achieved a validation root mean square error of 0.05410. That represented an 11.3% improvement over the single branch approach. That is the definition of algorithmic discovery.
It really is.
It's not just hyperparameter tuning. It's not just changing a learning rate from 0.01 to 0.001 and seeing as the line goes down. It is identifying a structural paradigm in one branch, a data processing paradigm in another, extracting the abstract logic of both, and writing novel code to fuse them together. That is exactly what senior human ML engineers do when they collaborate.
And it serves as the ultimate proof that non-greedy search combined with structured atomic operators actually works.
Yeah.
If the search had been purely greedy, focusing only on the highest immediate score, that physics GNN branch might have been pruned early on because its initial score was lower due to the data processing errors. By valuing novelty and progress, the system preserved that architectural innovation long enough for the crossover operator to discover it and utilize it.
Okay, so we've established that we have a highly efficient AI system running locally that beats giant frontier models at Kaggle competitions by intelligently merging complex code bases. But naturally, if you're an AI researcher listening to this, your next question is, does this transfer out of the sandbox?
Right, Kaggle is great, but it's not everything.
Exactly. Kaggle is a fantastic proving ground, but it's a very specific, gamified subset of machine learning. The data sets, even when messy, are bounded. The objective functions are strictly defined by the competition organizers. Does this recursive self-improvement capability actually transfer to open-ended scientific research?
That is the ultimate test, and the researchers evaluated it using Nature Benchlight.
Which is a very different beast.
Very different. This benchmark isn't about climbing a leaderboard. It's designed to see if an AI can independently match the published state-of-the-art results from actual scientific papers in the Nature family of journals. It tests the model's ability to replicate real-world scientific discovery.
They ran an ablation study here that I found really revealing, testing the model and the search framework independently. First, they kept the baseline search framework fixed, but swapped in the post-trained Frontis-MA1 35B model. When they did that, the matched SOTA rate, the rate at which it successfully replicated the state-of-the-art paper results, jumped from 50% to 70%.
Which proves that those 4 atomic operators, draft, improve, debug, crossover, are not overfit to Kaggle. The skills required to execute those operations generalize deeply to open-ended science tasks.
Then they did the reverse. They kept the baseline model fixed, but swapped in the OpenMLE Evo search framework. In that scenario, the match SOTA rate jumped from 20% to 50%.
Again, proving that evaluating progress and novelty combined with disciplined memory synthesis works just as well in a complex scientific context as it does in a structured competition.
And when they unleashed the full stack, the combined Frontis-MA1 35B system running the OpenMLE Evo framework matched the 7 out of 10 score achieved by GBC 5.4 on Nature Benchlight.
If we connect this to the bigger picture, this provides incredibly strong evidence for the core thesis of the paper. Execution-grounded post-training isn't just a neat trick to build a Kaggle grandmaster.
No, it's way more than that.
When an AI practices in a strict, verifiable sandbox, it develops skills that transfer to paper-relative scientific progress. The fundamental ability to write a hypothesis in code, execute it, read the logs, and structurally improve the architecture based on that feedback, that is the engine of AI research itself.
So what does this all mean for you as someone tracking the bleeding edge of AI? Consider the constraints we just discussed. We're looking at a 35 billion parameter model. In the era of multi-trillion parameter clusters, 35B is practically a pocket calculator.
Yeah, it really is tiny in comparison.
It fits on a single high-end consumer graphics card. Yet because it was given a mathematically disciplined Docker environment to experiment in and a structured, memory-efficient way to parse its own failures and successes, it can verifiably improve its own machine learning architecture.
It's remarkable.
It runs localized experiments and synthesizes complex structural insights and physically merges code bases to beat human experts at Kaggle and replicate Nature papers. If all of this is achievable right now, with just a 12-hour compute budget on an RTX 4090, it forces the massive shift in how we think about the future. Are we rapidly approaching a reality where the primary bottleneck to accelerating AI research is no longer scaling laws or parameter counts or even human ingenuity, but simply the sheer availability of executable sandboxes for these agents to play in?